this week's ARIS 360 weekly webinar using the Momentum tool. We'll take a second here to thank everyone for attending and to explain the format of this week's webinar. I'm going to demonstrate and explain how the Momentum tool is used for the first half of the webinar, and then for the second half I'll open it up for questions. So if you think of any questions during the webinar, just type them in the question area on your dashboard. So I'm going to start the webinar now and get the Momentum tool going. First of all, I'm going to open up a new scene. And this example that I'm going to give is actually a real crash. And if any of you have taken my class, you've probably done this example already. It was a test crash that was done at the exponent failure analysis crash test facility out in Phoenix, Arizona. And I want to say this test crash was done about 10 years ago. It was involving two 1994 Chevrolet Caprice Classics. One of them was brought in at 60 miles per hour down a track, hooked to a cable underground, and the other one was brought in at a 90-degree angle and was struck in the driver's side, toward the left rear door there. The slow-moving car spun out and came to a rest, and the bullet car also spun about half a turn and then rolled to a stop. The reason I use this crash is because it's a very good momentum type crash that has really good evidence to it. And this is a really good way to validate the tool, because we have vehicles that came in at known speeds, and we see if the tool can actually come up with those same speeds. So I'm going to bring in the evidence right now, and this evidence is total station measurements that were measured at the scene. I'm going to bring them in right now, and I'm going to back them out, and I'm going to slide them over so we have some run up, and I'll color all the points black. And I'm going to also connect them. So you see that we have some measurements from this crash. What I'm going to do now to facilitate my using the tool is I'm going to place all of these measurements and all of these lines that are connected from the measurement to measurement. I'm going to put them all on a different layer. And the reason I do that is so that when I put the Momentum tool over top of these, then I want to move the tool around and adjust it, I don't keep clicking on these measurements, because I can click on these points every time I click. And sometimes if you get the Momentum tool over top of that, you'll get the lines instead of the tool, and you don't want to do that. So I'm just going to go and select all of these items that I put out here just by boxing it. And then I will right-click and change layer. And we'll call this evidence. I'll add it to the layer, then I'll go to the Layer Manager, and I'll lock it down. That way I cannot click on it. Now I'm going to go up and I'm going to get my Momentum tool, and it's located in the Analysis section. It's the basic Momentum tool. I'll click on it one time. If you click more than once, you're going to get more than one tool out there. So you just need to click once to get it out there. And what this tool does, it's a graphical tool that will keep track, very accurately keep track, of angles, either approach angles or departure angles. And it'll keep track of those angles to the nearest 100th of a degree. It will also keep track of distances, and it will keep track of those distances to the nearest 100th of a foot. It will also keep track of the weights of the cars, and the weights of the cars are determined by which car you select from the database. And then the database will indicate how much the car weighs, and you can add or take away any of that weight depending on what the actual test weight of the car is. It will also allow you to assign some kind of a deceleration rate after impact. And you can do it one of two ways. You can assign an average friction for the whole distance from impact to rest, or you can assign the ground friction there and then assign a braking efficiency for each tire on each car. And then spin the car around and it will calculate the spin out for you. Either one, you can do it either way. And you can have multiple friction zones after impact if you like as well. So what I'm going to do now is I'm going to assign the cars. I'm going to go to the Vehicles section on the left Properties panel. I'm going to click on Select from Database. And I'm going to select the manufacturer of the car, which was a Chevrolet, the year, which was 1994, and the model, which was a Caprice. And these were old police cars. And then I'm going to click on Insert, and that car will be inserted into the diagram on top of the Momentum tool. I will go to the second vehicle. It's going to remember the vehicle. It's the same type of vehicle anyway. We will insert it. And we can color these. I'm going to make one of these red just so that we have two different colored vehicles. Now down on the left Properties panel, you can assign some load. There's your published weight according to the vehicle specs database, 3,981 pounds, and we had a test weight of 4,320. So I'm going to add 339 pounds to each of these cars to get it up to that test weight of 4,320. Next thing I'm going to do is I'm going to go to Details. And then this is where we can set our after impact deceleration rate. Now if I wanted to do an average, I can click on here and make my average, which what I'm going to do in this case. But if I didn't want to do the average, if I wanted to give it ground friction, which was about a 0.7, I can check the Adjust for Spin, and I can assign percentages of braking to each tire on each wheel. And as you spin the car, you'll see these adjusted drag factors change. So depending on how much spin you had and how much braking you had on each tire, then you'd get the proper deceleration rate that you're looking for. In this case, I'm just going to check that, and I'm going to give it an average. And I came up with this average based on no braking going on in the cars. They were simply just spinning out. I looked at the deceleration or the marks after impact, determined that all four wheels were free to rotate. There were times when the cars had a full 0.7 when they're sideways, and there were times they didn't when they were rolling straight. So we went right in the middle of that, 0.42. Now remember, the vehicles were doing 60 and 20. So let's see if I'm right. So now I'm going to grab the tool. By the yellow star will move the whole tool together, and I'm going to place it over on top of my evidence. Now let me explain the evidence for a minute. Let me move the tool out of the way. This straight horizontal line was the cable tray. So that's the approach angle of the car. There was an underground cable that was dragging this car in, and it breaks away as soon as they crash. Same thing here. This is a above the ground cable that was dragging the slow-moving car in. So I have really good concrete evidence here of approach angles, really good concrete evidence. And we have really good concrete evidence of departure angle because this is the actual evidence that the car left. So I'm going to bring the whole tool with the cars on it over on top of my evidence and line them up. Now you want to have this red line, which is the approach of the red car, on that cable tray. You want the blue line on the vertical line, which is the cable, the above ground cable. Now these cars, where they hit, the red car hit the blue car toward the back. Right here, just like that. And this is my damaged centroid, so I'm going to put that right there. Now, the red car ends up over here, I'm sorry, it's right there. The blue car ends up over here. So I've got them into a pretty good location, but I'm not exactly there yet. So I'm going to take the red car. I can look at the black marks, and I can see that the red car spun counterclockwise a half a turn, because I can follow the rear tire. This is the rear tire mark. It comes around and ends up on this side and slides backwards. So I'm going to rotate this car around. Now you can see from the measurements I took at the red car, we have point number 47 and 48. That's the back rear corner of the car. That's what I'm really interested in now, because that's how far the car went. Now this dark red line, that's the path. If I grab these green grips, I can put that path right in the middle of the evidence, is what I want, because that's what this car did. This car went right straight down, and this red line should be right down the middle of the evidence. Now this green grip controls departure angle. Once I move that, notice the yellow lines will line up right up on top of the black ones. That's what you want. You want them at impact and at rest to be as close to those marks as possible. In between, it's not so critical, because what momentum is looking for is departure angle and distance. It doesn't care what happens in here. And whether you do it by hand or whether you do it using the tool, it's looking at distance and departure angle. So I've got my red car pretty good now. Now I'm going to look at the blue car. If I adjust the blue car as it was at impact, I can look at these black lines, and I can tell that the car rotated up to here. These are the back tires. And that's a half a turn, actually a little more than a half a turn. Then the tires came over to here. There's another half a turn. And then they ended up back over here. That's another half a turn. So if I rotate this car 1.5 times, there's one, there's a half, and of course a little more, and then put it right on top of the marks. And this is where you want to zoom in so you can really get this accurately. Very accurately. So now I'm going to zoom out, and we can see that this departure angle, if I was way over here, that would be incorrect. If I was down here, that would be incorrect. If I was right down here in the middle of the evidence, then that would be correct. Okay? So now I'm going to back out, and I'm going to look at my tool on top of my evidence. I'm going to, again, check it, make sure everything's lined up. Is the approach angles good? They look good to me. Departure angles look good. Distances look good. So now all I have to do is go over here to results, right up here on the left property panel. Click on results, drop down here to output, and my red car is showing that it's going 59.91 miles per hour. And actually at the test crash, it was doing 60. So I am less than 1/10 of a mile an hour off. The other car, the blue car, I look at my results. It's doing 19.94 miles per hour. At the test, it was right at 20. So again, I'm less than 1/10 of a mile an hour off. So I'm very satisfied with this. And you can see if I change any of this stuff, if I make this departure angle incorrect and go that way, look at my speeds now. Look how they changed. I went from 60 just about to 50 on the one car, and went from 20 up to 28. And as I move this, you can watch those change. They're live. Okay? So if you make a mistake with your departure, you can see how sensitive that can be. Very sensitive. Either one. If I'm over here, that's not correct. Look at that, 58 and 28. If I'm down here, well, that can't be correct. You're going to get this this error notification up here, because it's physically impossible for that to happen. So let's go back up and get our spot right where we are, and there we are, 59.9 and 19.97 again. So we're right there. And the same thing goes for approach angle. If we change our approach angle, things can happen. And everything is live. Now, when we're all done with this, you can look down here and click on Print Report. And it's going to print a full report of everything that we've done. And I'm going to check all the boxes here, because you can check and uncheck things that you either want to see or you don't want to see. This is the first page of the Momentum Report. It will give you 2 columns of results. The first column is going to be all the inputs that you used. Okay, every input that you put in here is going to show up here. So it's going to have the weights of both cars. It's going to have the approach angles of both cars. It's going to have the departure angle of both cars. And it's going to have whatever post-impact frictions or adjusted drag factors that we used for both cars. That's your first column. The second column over here is going to give you all your outputs or your results. Your impact speeds are going to be listed up on top for both cars. Then we're going to drop down. It's going to be the velocity of the damaged centroid. You'll have your separation speeds, your delta V's, your PDOFs, and your separation yaw rates. The next page, simple vector diagram, showing you just the angles and distances. Next page is your vector sum analysis. 100% of momentum in equals 100% of momentum out. Next page, we start to get into our math. This is the post-impact separation velocity for V1. You see the formula, the terms, the values, and all your longhand math steps. The next page, same thing for vehicle 2. The next page, impact speed for vehicle 2. There's your momentum. There's the formula that you can use with Aris Genius. You can use it with doing it by hand. You can put it in any other momentum calculator, and you're going to come up with this answer down here. It's calculated out for you, and this is the longhand results right here. Next page is going to be impact speed for V1. There's your momentum for V1, all the way down to the speed. Then we have a delta V for the first car, a delta V for the second car. We have a principal direction of force for the first car, principal direction of force for the second car. There's also going to be overview of solving separation velocities at the damaged centroid. There'll be a couple of pages of that to get your impulse. There's going to be an overview of calculating average friction due to vehicle rotation, should you choose to go that route. There's going to be a momentum animation report for each car. And this animation report will tell you the coordinate location of center mass for each vehicle every quarter of a second from impact to rest. And you get that for both cars. There's a momentum vehicle specifications report. This is the report that listed how much the car's published weight was. Also has all its dimensions. And then finally, the very last page is a reference page that gives you a brief explanation of how the tool works. And I want to also point this out here. Users of the system must always have well-documented evidence confirming the basic set of information that provides the input variables to the solution. So you need to know where the vehicle positions were at impact. You need to know where the orientations at impact. You need to know their rest positions, their weights, and their departure and approach angles. And you need to know some kind of road friction information for post-impact. This, you have to know this whatever way you do this, whether you use this tool or not. So that's the momentum tool. And additionally, we can jump into 3D if we want, and we can actually play a little animation. it's going to create an animation for you. So there's the cars coming in at their momentum speeds of 60 and 20 and going out at their separation speeds and going right to their points of rest at the specific amount of time it takes to get there. So that's a momentum tool. And I'm going to open it up to questions now, and I see there's a bunch in here, so let me go stretch this box out so I can see the questions here. Oh, we just got a couple questions. First question: when placing vehicles, should they be positioned at maximum engagement or initial contact? That's a good question. You can probably do it either way. I've got them at a little bit past contact, but if I went into maximum engagement, is it going to affect my speeds at all? Not hardly. So I don't think it matters. It probably would matter minutely, but with this particular car, you're not going to know exactly where maximum engagement is unless you know how much crush was there, what the exact amount of crush was, and have that measured. So this can be kind of an estimate, if you like. It's not going to affect your results more than 1 mile per hour one way or the other, or maybe even a half a mile an hour. Okay, so the next question. Can you explain the friction zone, please? Okay, let's go back to the friction zone. Right here, I'm going to take vehicle 1, for instance. I've got this friction zone from impact to rest having an average of 0.42. That's from start to finish, an average. So there's going to be times when that friction is up there because the car is traveling sideways and the vehicles tires are sideways, so they're not rolling. But then they start to roll again as soon as the car rotates around. So I used an average friction of a 0.42. Now, if you wanted to put a 0.7 here, let's say that you made the mistake and you said, okay, the friction after impact is 0.7. What does that do to my speeds? Well, look at them. Now we're doing 77 and 27. That is not correct. The friction zone after impact, and I don't like to even call it a friction zone. It should be a deceleration rate. Because what are the cars doing after impact? Are they skidding? Are they just freewheeling? Are they bouncing and sometimes they're off the ground? In this case, all three of that stuff's happening. So this is the most important and probably most difficult part of any momentum calculation to get right. What did the cars do? And this is where everybody's going to have their own opinion. This is the place you'll get attacked, whether you do this by hand, whether you use a tool, whatever. Because I can assign whatever friction I want there to get whatever speed I want, really. I could do that. But I've got to justify why I use that deceleration rate. So when I used a 0.42, I can justify that. Because ground friction is a 0.7, rolling friction on these cars was somewhere around a 0.2, I went right in the middle of it. Because you know what? Sometimes they were rolling and sometimes they were sliding sideways at the full friction. So I can justify using that average in the middle somewhere. Okay, next question. Since the physical evidence is key, what do you have to do to make the tire lines match the evidence? Well, for momentum, what's key here, you're right, the physical evidence is key. But what part of the physical evidence is key here? I'll tell you what part it is. Departure angle, that's key. Point of rest, that's key. What happens in the middle, does that matter? Nah, it doesn't matter. Now, these yellow lines do not line up on the black ones, do they? They don't, because the momentum tool uses symmetric rotations. In other words, it's going to be constant rotation. It's going to be the same rotation from start to finish because we're just using one segment. If I were to do an animation on this, I'd divide this up into two segments and make the yellow lines follow the black ones. But for the momentum tool, momentum doesn't care about rotation. It cares about approach angles. It cares about departure angles. It cares about weights of the vehicles, distances they went after impact, and whatever friction you use to determine the post-impact speed. Okay, next question. Given the location of the initial crash and probable damage to the left rear wheel, what was the actual damage and effect on drag? Well, the damage, the front end of the car was damaged, and the left side of the car was damaged. Now, what kind of effect did it have on a drag? I couldn't tell you. I don't think anybody can tell you. You know, I don't think that's something that we don't know, and I don't think we even need to know. Because what I did is I gave an average friction due to vehicle rotation, and I came up with the right speeds. The tool came up with the right speeds. Okay, let me look at another question here. Any comments about the drive wheel deceleration rate of X versus rolling friction? I have no comment on that at all. These vehicles were not running. They were in neutral, so I don't believe there was anything going on there. As a matter of fact, when you look at the video of this, when the red car hits the blue car and the blue car spins its first spin around, the rear tires aren't even on the ground. They're off the ground for a part. So what kind of deceleration rate is there? You're down around 0. For a very short distance, but you're down around 0. Okay, next question. You have the advantage of knowing the actual conditions for this wreck, so I can't read this. Matching the speed is easy. Matching the speeds is easy, but you showed a range of plus or minus 15 miles per hour based on bad input, and that is unknowable. I don't understand that question, Phil, about plus or minus 15 miles an hour. I don't think I said anything near that. Maybe you want to clear that up a little, Phil? Oh, when I showed 77 miles per hour, that's by using a friction of 0.7 instead of what I used, a 0.42. If I used a 0.7 friction, that would mean that both of these cars had 4 wheels on the ground locked the whole way from impact to rest. Then you would get 77 miles per hour. But that wasn't the case. So that's why we have a friction of 0.42, and it comes up to the 60 and 20. Let me go back and fix that for you. I'm going to go to details. Right there is 0.7. Let me put it back to a friction that is what we really had out there after impact. And now we have our results at 59.8 and 20.9, somewhere around there. The other input, Phil, was changing the deceleration rate and raising it all the way up to a 0.7. This tool is doing nothing more than what you can do by hand. It's just doing it faster, easier, and quick and more accurately. Because when I say more accurately, you're getting the angles to the nearest 1/100th of a degree. If you were doing this by hand, you wouldn't even come close to that. You're getting the distances to the nearest 1/100th of a foot. Now you probably could come close to that if you used a total station. Do I find people want a sensitivity analysis in court? I've never had that happen. I'm not going to say it doesn't, but it's something that I would like to see myself. Like if I had a different deceleration rate, what would my result be? If I had a different approach angle, what would my result be? And I would want to know that immediately, and this tool can do that. How do you adjust the different surfaces post-impact? Okay, good question. Right now I've got, let's say that we have a line drawn right here. I'm going to draw a line. And I'm going to say that that line is going to represent the pavement. So once a vehicle goes off the pavement, there probably, or most likely, would be a different deceleration rate off the pavement. So if I want to change the deceleration rate off the pavement, all I have to do is go into my details here, go into my drag factor after impact. Now I'm going to say this red car is going to have a different deceleration rate once it gets off the car here. So when I go into friction zones for vehicle 1, here's my zone 1. It's a 0.42 all the way. I'm going to add another zone. So there's the second car's there. And I'm going to move the car over to here. And let's rotate it around. Hold on there. Make sure we rotate it around here. So we're going to rotate it around. I need to go the other way, I think. Let's go this way. There we go. Oh, wrong way. So let's say that we're going to have it right after impact here. You know what? This is probably what I got to rotate around. Yeah, let's go the other way. Okay, let's move this one around here. And then let's take this car and let's fix it. I went the wrong way again. There we go. So we've got part of the car for the first impact, for the first segment is a 0.42. Now maybe for the second segment we want it to be lower than that, maybe a 0.3. So by doing that, I'm going to adjust my speed a little bit. See that? It went down just a bit because I didn't adjust it that far out. But that's how you can add multiple zones. And I believe that's the question you asked. Okay, I've got a question. Would you change the post-impact to 0.47 and see what the impact speeds were? Okay, so let's go to details here. And right here, there's 0.42. And you can see we're 58.68. And actually, I've got, this is only for zone 1. We're going to make it 0.47, I think somebody wants. So you can see the higher you go with your deceleration rate, the higher your speed is. And we'll do it for both of these. So you raise it a little bit, you're raising your speeds a little bit. And you can see this instantly. If somebody says on the other side would say, okay, I used a 0.6 or a 0.55. Well, you can see what he came up with, and then you can see what you came up with. And then there's going to be the argument, who's right. It's going to be who can justify why they use that deceleration rate better than the other guy. Anybody have any more questions? Okay, we have a Another question. What basis do you use to figure the free drag factor? So rolling friction, I guess, is what you're asking. In this case, we did a test for those cars. We took the cars over a measured distance and got them up to a speed. And then over the measured distance, what was their speed? What did it go down to? And we did a calculation to see what their deceleration rate was, just simply coasting. In this case, I think we did it 3 times. It was a 0.19, a 0.20, and maybe another one. It was right around 2.0. Maybe it was a 0.21, 0.20, and 0.19. So we figured a 0.20. And this was 10 years ago, so I'm trying to rack my brain to remember what it was. But we did a rolling friction test on the cars to see what the rolling friction was. Okay, another question. In the advanced results menu, can you put in an instant delta V instead of a friction zone? Yes, you can. Yes, you can. And when would you want to do that? The answer to that would be if the car hits something. Let's say the car hit a curb. There's going to be some kind of delta V by the car hitting a curb, or the car hitting something else. Maybe it hit a tree and knocked the tree down but kept going. Or maybe it hit a tree and stopped. You're going to have to determine what that delta V was, and then you would go in here and check it. I'd add another zone, make it an instant delta V, and then put whatever the speed was there. Or not, I'm sorry, not there, right here, whatever the speed would be. If it was a 5-mile-an-hour delta V or a 10-mile, let's say the car got down to 10 and then hit the tree and then stopped. Well, there's a 10-mile-an-hour delta V there. And it would go ahead and associate that with here. So if I did that now, put in 10, look what it did. It knocked my speed up now to 73 miles an hour because that car would have kept going if it didn't have that delta V. So yes, you certainly can do that. Any other questions? When do you use basic, advanced, or collinear analysis? Well, what I've shown you today and what this webinar today was on your basic momentum, and that's what we did. Now, the advanced momentum, the SAMI, that's going to put in some damage for you. It's going to add the damage to the cars. So if you want to see the damage, you can use the SAMI one. The collinear one, that's going to be head-on collisions or rear-end collisions, not angular momentum like this. It's a totally different formula. And we'll do webinars on those two in the future. Just keep an eye on our website for the different subjects that we're going to conduct our webinars in. We kind of changed our format a few weeks ago. So ahead of time, you're going to know what the webinar is going to be about. So if you don't have any questions on that, you don't have to attend. If there's something you really want to be in, then you can attend that particular webinar for something that you're interested in. And if anybody wants a specific subject to do a webinar, that we want us to do a webinar on, simply email me at mgreenfield@aris360.com, and I'll be happy to make up a webinar and show you how to do certain things. Any other questions? I've used this tool in several of my own crash reconstructions where I didn't know what the speeds were, and they came out pretty good. I had a crash where a car pulled out in front of somebody else, similar to this, and I used the speeds of the cars that I obtained from the airbag module downloads, and the speeds I came up with matched those. So that's just another nail in the coffin, because a lot of the airbag module downloads, the CDR downloads, they're going to give you impact speed and possibly even speeds prior to the crash and delta V's and that sort of thing. So you can use that in conjunction with the momentum tool also. Are these going to be available for reference? Are you talking about the webinars? Yes, the webinars are, I'm recording today's webinar, so hopefully we're going to have a list on our website that you'll be able to click on these webinars at any time and view them again if you want. I think that's what you're asking. Okay, anybody have any further questions? Okay, another question. If instead you used adjust for spin, what would that look like? Well, let's go ahead and take away these instant ones here, and let me, yeah, we're good now. Okay, let's go to results, and let me go in here, and let me go back to details, and if I used adjust for spin, let's go back to the 0.42. This is what I used for this crash, 0.42, and I had roughly 60 and 20. Now, if I said, okay, I'm going to adjust for spin, and I'm going to use the 0.7 ground friction that's out there, and I'm going to say that the vehicles had, I don't know, for the rear tires, we had 0% braking on the rear tires, and 0% braking, no braking at all. Okay. Now on the front, maybe I got 10%. And where am I getting these numbers? I'd have to look at the tire marks on the ground and say, okay, what are these tires doing? Okay, what are these tires doing? Now we're defaulting it. Let's say we had 0 braking all the way around. 0 braking all the way around. Okay, so based on our spin, let's take this back here. And let's take this one back. Okay, so there's no spin right there. Now, if we spin this half a turn, you're seeing it's getting an adjusted drag factor of a 0.43. So even with the spin analysis, with no braking, I was really close at that 0.42. And on the other car, if I spin it, I'm going to be pretty close as well. That one's got a 4.7. But still, I'm 1 mile an hour off the original speeds that they were, even using my spin out. Now, what did I have a 4.7 on this one? I don't know. I don't know. I just gave it a 0.42 for both of them because you know what? They were just spinning. But the actual speeds of these cars were 60 and 20. They weren't 61 and 20, 22. So this is a little high. Any other questions? Okay, somebody says put 20% on all four. So if I go 20, that's what we started out with, is 20% on all four. That's what we defaulted at. And we have a 0.47 and a 0.5, and you're getting speeds of 64 and 22. In this case, that was not correct. Too high. Too high a friction after impact for this crash. Everything that we used here in this tool is concrete evidence except the deceleration rate after impact. That's the only place that you will get attacked if you're going to get attacked anywhere. Why did you use that deceleration rate? And it's whether you use the tool or whether you do it by hand, that's the place they're going to go after, because that is the most sensitive. I've seen people on the other side, when I was doing fatal crashes in Phoenix, get their deceleration rate after impact down to about a 0.2 or something like that, just so that their guy wasn't going so fast. And I've seen it on the other side where sometimes people put a 0.7 there, and their speeds are so high and they're not that fast. So there's where you're going to get attacked, no matter whether you use the tool or not. It's just the nature of the beast. Any other questions? Is there a derivation from collinear that this works for? Yeah, we have a collinear tool as well, but we're not covering that in this webinar. Any other questions? Oh, what angle does this work for? I believe that's the question. Any angular collision, and I want to say anything from right angle, maybe go 45 degrees one way or 45 degrees the other way. But once you get, pretty close to head-on or pretty close to a rear-ender, then it gets way too sensitive. So you want to use the collinear version of this. This is angular. This is 360 angular momentum. So, don't. If they're coming in, if you watch the screen here, if they're coming in something like this, I probably wouldn't do it. It's even going to tell you this is not recommended for 360 momentum. So let's go back down. Right about there is where it's going to say OK. All right. Okay, you have a question, is there a reason I didn't use 100% braking for adjust for spin? Well, if I used 100% braking if I adjust for spin, watch what's going to happen. That means all four wheels are locked the entire time, and you're getting the full 0.7 the whole time. That would be as if I took this drag factor and made it 0.7 back when I was doing the 0.42. It's the same thing, and we got up to 77, and again, using this drag factor 0.7 right here and checking adjust for spin, you're going to get a 0.7 right here. There's no point of doing adjust for spin then. You can just uncheck this and leave it at a 0.7. It's the same result. Is collinear another module? Yes. If you go up to the analysis section, we have collinear momentum right here. And if I'll bring one of those out there just to show you. It is rear end and head-on collisions. So there is another module. It's called Collinear Momentum, and it's out there. It's for rear-enders and head-ons. Ones you have less of an angle that you have here. Any other questions? Okay, this was a follow-up from the why didn't I use 100% braking and adjust for spin. And I'm getting another example of 60% for front at 30% each and 40% at 20% each for front and rear. Oh, okay. I see what you're saying. And you can do that, but that's if all four wheels were locked up. You could do that. You'd come up with probably a little bit different speed, but you could do that. Do I have a recommendations on reading tire marks for percent of braking? No, I don't have a recommendation for that. It's just experience out there. You're looking at the marks. If they're braking and you can tell, first of all, if the marks are thick and black in the road, there's no striations, you got a pretty good indication that there's 100% braking on that wheel. If you see some black marks, a gap, black marks, a gap, black marks, a gap, well, you're going to have something less than 100%. If you see striations the whole time, well, then you probably don't have any braking. It's just scuffing. So, I mean, it's just looking at your evidence in the road and determining what you have. Sometimes the damage of a car will lock a wheel down. Well, then you know that you have 100% braking on that wheel because that wheel's not turning anymore. It's totally locked. The damage has got it locked down. Sometimes the front of vehicles, you get damage locked down because when they hit another car, they get crushed back and now they're locked. They can't move anymore. You can assume 100% braking on those two wheels. Any other questions? Okay, everyone. Thank you very much for your attending the webinar, and look for us next week, and have a good week. Thank you.